If you haven't done so yet, please pause the video and attempt to solve the question on your own before listening on. The first thing we want to do in solving this question is to draw a picture of the arrangement of charges. So as the question describes, we have a proton located at the origin, and we've labeled that proton Q1. And then we have a second proton located at 6 femtometers across the x-axis. The question thankfully tells us that a femtometer is 10 to the minus 15th meters. Now in part A, we're going to be calculating the electrical potential energy associated with the configuration of these two charges. Now we know that the electrical potential energy of 2-point charges is given by this expression here. We're simply going to be plugging in the charges, and since these objects are protons, we'll use the standard unit charge of 1.6 times 10 to the negative 19th coulombs, and then the distance between the charges was given to us as 6 femtometers. So we'll go ahead and plug in the known values. And when you simplify that on your calculator, you should get approximately 3.84 times 10 to the minus 14th joules. So that would be the correct answer to part A. In part B, they're bringing in an alpha particle, which is described in the question in the parentheses, and they're placing it at a coordinate 3, 3 femtometers, and we're now asked to calculate the electrical potential energy of this 3-charge system. Now we have to notice that there's actually 3 pairs of charges that we have to make the calculation for. We have Q1 paired with Q3, we have Q3 paired with Q2, and then Q1 is paired with Q2. So we actually have to set up the electrical potential energy equation that we did in part A, but do so 3 separate times, once for each of the pair of charges. So for example, the first electrical potential energy between charges Q1 and Q2 is given with this term right here, and then between Q1 and Q3 is the second term, and then between Q2 and Q3 is the third term. Notice that the first term is the exact same potential energy that we found in part A, so we can replace that with the following term. We'll use PE sub A. Also notice that the distances labeled R13 and R23, whatever they are going to be equal to one another because of the symmetry of the arrangement. So we can actually call the second denominator R13. Now because charge Q1 is a proton, we know that its charge is the elementary charge that we can call E, and the same thing for Q2. Notice that Q3, which is that alpha particle, has a charge of 2E. So we would actually want to substitute in 2E for the charge on Q3. We then notice that E times E is E squared, so we can make that adjustment in both terms. We could then add these two terms together because they're like terms and they have common denominators. Now we're essentially ready to just plug in and calculate the potential energy. We just have to get the distance that we've labeled R13. And so we'll notice, if we dropped a line straight down here, that this distance right here is 3 femtometers, and that this distance would also be 3 femtometers. If we did the Pythagorean theorem on this, we would see that the hypotenuse, or this R13, would be 3 radical 2. So that means that the distance, R13, is going to become 3 radical 2 femtometers. So we went ahead and plugged in all the known values. Once again, note that PE sub A is the same potential energy we found from part A of the question. Also notice that we converted that 3 radical 2 femtometers into meters by multiplying by 10 to the minus 15th. And so now we can just pick up our calculators and process this computation. And we would get a value of approximately 2.55 times 10 to the minus 13th. And since this is energy, it would once again be in joules. So that's the correct answer to part B. Now, for part C, if we allow the alpha particle to escape, then the change in potential energy will simply be the potential energy we had found in part A minus the potential energy we had just found in B. Hopefully that makes sense, because remember, in part A we had the 2-charge system, in part B we had the 3-charge system, and so to get the difference in potential energy, we would simply subtract the potential energies associated with those charge systems. So we'll plug in the value we found in part A and the value from part B, and we obtain approximately negative 2.17 times 10 to the minus 13th joules. So that's how much potential energy would be lost. Now energy, when we say it's lost, it just doesn't disappear, of course. So what happens is the potential energy that was lost will be converted into kinetic energy. And now we know kinetic energy is equal to 1/2 times mass times the speed squared. The amount of potential energy lost was just computed, so we can plug that into the left side. The mass of the alpha particle was given to us in a standard unit, so we can plug that in for m. And then we can easily solve for the speed v. So we would multiply the 1/2 by the 6.64 times 10 to the minus 27th, and then divide that result over to the left side. And then we would take the square root of both sides to solve for the speed v. And we would see that the speed is approximately 8.08 times 10 to the positive 6 meters per second. So that would be the correct answer to part D. Now in part E, we're taking the 3-charge system, and then we're letting the 2 protons go to infinity. So all that's left is just a single charge. Now in a single charge situation, there's no pairs of charges remaining. So that means that the final potential energy in that scenario would be 0. We already calculated the potential energy in the 3-charge system in part B of the question. So all we have to do is subtract these 2 potential energies to get the energy lost. So 0 minus the 2.55 times 10 to the minus 13th joules that we found in part B would of course just be negative of the potential energy found in part B. Now again, that energy doesn't disappear, it's converted into kinetic energy. Now we have to note that the amount of energy is split evenly between the 2 protons. And so if we're going to calculate the speed of just one of the protons, we actually have to set the kinetic energy of that proton equal to half of the potential energy of B. Kinetic energy, once again, is 1/2 times mv squared. Because 1/2 appears on both sides of the equation, we can eliminate it algebraically. We'll divide both sides by m and then take the square root. Again, the potential energy at B was 2.55 times 10 to the minus 13th, and then the mass would be the mass of a proton, which is approximately 1.67 times 10 to the minus 27th kilograms. And we get a speed of approximately 1.24 times 10 to the 7th meters per second. So that would be the speed of each proton in part E of the question. Thanks for taking the time to watch the video. If you liked it, please click the thumbs up icon and subscribe to the channel. You're welcome to send your own question into the email address on the screen, and I'll do my best to post the solution to it on YouTube.